thanks for watching. And so far in our PDE adventure, we discovered two main equations, or two main protagonists, if you wish. On the one hand, we have what's called the heat equation, which is ut is duxx with some initial condition u of x0 equals f of x, which, remember, models the temperature of an infinite metal rod. On the other hand, we have what's called the wave equation. In this case, utt is c squared uxx with initial position phi of x and initial velocity psi of x. And what we want to do in this video, we want to compare them, and in particular we will see that this little change here, changing ut into utt, has a huge effect, almost like a butterfly effect. And so here are the 5 main properties we want to study. First of all, existence uniqueness. Uniqueness. In other words, does each equation have a unique solution? And for the heat equation, existence, yes, there is a solution which we found. I would like to remind you what it is. So u of xt is just a convolution of f with the heat kernel. So f star g xt, which in this case is 1 over square root of 4 pi dt, integral from minus infinity to infinity of f of x minus y, e of minus y squared over 4 dt. dx. Sorry, dy. So in other words, you just convolve the initial condition with the heat current. So we do have at least one solution, and uniqueness, if you remember the energy method lecture, the answer is yes, sarcastically, meaning there is uniqueness provided u doesn't grow too fast. So yes, provided, I believe, u of xt, so u is less or equal to cea to the x squared. So provided it doesn't grow super exponentially, then we do have uniqueness. And of course, on the finite rod, we have uniqueness as well. On the other hand, for the wave equation, the answer is yes in both cases. So for wave, existence, also yes, because we do have D'Alembert's formula. So u of xt is 1/2 phi of x minus ct plus phi of x plus ct plus 1 over 2c integral of x minus ct x plus ct psi of s ds. In other words, the initial position splits into two, one going to the left, one going to the right, and the initial velocity has a bigger and bigger effect on the solution. And for uniqueness, the answer is also yes, and that's by energy methods. So we've shown this in a previous video. So for our purposes, for both equations, they're similar in the sense that yes, there is pretty much a unique solution. The next battle, or the next proposition, is smoothness. And the question is u of xt always smooth? In other words, can you always differentiate u as many times as you want. And here is where both equations differ. Because remember, for the heat equation, the answer is yes, meaning that no matter what F looks like, so even if F looks like this, then the solution to the heat equation becomes automatically smooth. U of xt. And remember, that's because all the derivatives fall onto the super smooth function e of minus x minus y squared over 4dt. However, for the wave equation, the answer is no. And you can see this from the formula for the wave equation, because if the initial condition has a kink somewhere, then that kink still gets transported. So for instance, if phi of x looks like this, where we have a corner here, then u of xt, well, it splits into two. Yes, again, one moving to the right, one moving to the left. And you can see that that kink is still here. So any non-differentiability still gets transported, which, in my opinion, is pretty bad. We do like smoothness a lot. Okay, so that was the second battle. Now the third battle is about speed of propagation. So property 3 is speed of propagation. In other words, if the initial condition is positive somewhere, is the solution positive everywhere? So once again, for the heat, if, again, f of x is greater or equal to 0, and, again, the initial condition is positive somewhere, then the solution, in fact, is positive everywhere. At least for positive time. So, in other words, what this looks like, if your initial condition f of x has a little bump here, so here it's positive, then the solution immediately becomes positive. And that's because you're integrating a non-negative function that is positive, so the integral becomes positive. And once again, what's the interpretation? So suppose you are here, and some alien lights up a match light years away, then you would immediately feel the effect of that heat, because your temperature here would be a bit positive. So in our model, heat propagates at an infinite speed. But for the wave equation, that is very different. In other words, if, for instance, phi of x is greater or equal to 0 and phi of x is positive somewhere, this does not imply that u is positive everywhere. And again, I want to illustrate this with a picture. So if phi of x, let's say it's 0 everywhere and suddenly becomes positive, then remember, things propagate. It's not true that the solution is positive everywhere. Because, for instance, you might be here and your value here is still 0. And once again, in this scenario, what this means is, if an alien light years away emits a sound, or just says, then it'll take some time for you to feel this. So it's very interesting, while heat propagates at an infinite speed, sounds or light do not do so, which is kind of cool. Okay, next one, the backwards equation. The next one, so the backwards equation. In other words, can you go backwards in time? In other words, if I tell you, for instance, what the heat is at time 1, can you tell me what the heat is at time 0? So if I give you u of x1, can you tell me what u of x0 is? Yes. And for the heat equation, remember, the answer is no, because the heat equation is generally irreversible. So, in other words, if I tell you, for instance, what the heat is at time 1, like this, u of x1, in general, there's no way of figuring out what the heat is at time 0. And again, one reason for this is the backwards heat equation is ill-posed, or if u of x1 has a kink, then in general no initial condition can tell you, what happens, because heat equations are automatically smooth. However, for the wave, the answer is in fact yes. So let me just illustrate. For instance, if we know u of x1 looks like this, and remember the wave propagates to the left and to the right, well, to make it go backwards, just move the wave in the other direction. So in other words, if those triangles are going to the right, to find the initial condition, move those triangles to the left, and you can figure out u of x0. So that's also a main difference between the heat and the wave equation. And last but not least, let's figure out what happens for long time. So prop 5, long time behavior. So in other words, what happens as t goes to infinity? And remember, for the heat equation, we have that u of xt goes to 0 as t goes to infinity. In other words, suppose the heat equation looks like that. U of xt, then as t goes to infinity, so as t gets larger and larger, we do have that eventually things slow down. And this is simply because the heat kernel itself goes to 0 as t goes to infinity. And by the way, now that we've done energy methods, an indication why this is true is also because the energy is decaying. Because E of t, remember, is 1/2 integral of u of xt squared dx, let's say for minus infinity to infinity, is decreasing. So not a proof, but at least an indication that you might go to 0. On the other hand, once again, for the wave equation, this is false. So wave, it is not true that u of xt goes to 0 as t goes to infinity, Because there are many reasons to see that. One is, well, what happens to the waves? Well, literally, they go to the left and to the right, so those waves will never be zero, even after a long time. There will always be a point where the wave is positive, for example. Another way to see this is because of the contribution of psi. Because if, let's say, even if the initial position is 0, then u of xt is integral from x minus ct to x plus ct, psi of SDS. But as t goes to infinity, this actually goes to the whole area of psi of SDS, which is generally non-zero. So once again, that's because this might be the initial velocity, and that might be a point x. And remember, the contribution is over a bigger and bigger interval. So this area is just getting bigger and bigger, and in particular, it's not true that it goes to 0. And last but not least, another reason for this is because of energy conservation. Because we know that this energy, 1/2 integral of minus infinity to infinity of ut squared plus cux squared dx, this is constant. Now, we know that this is constant and presumably non-zero. Now, if this is true for all t, it would be true for t equals infinity. So in particular, this whole integral at t equals infinity is positive, which tells you that either ut or ux cannot go to 0. Because otherwise, this integral would be 0. And in particular, this also implies that u cannot go to 0 as well. So once again, very, very different. All right, I hope you like this little comparison between the heat and the wave equation. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.